Alright, on this video we're going to talk about ambiguous triangles. I've put up here something I took from a website I found from Rochester Institute of Technology, and it's discussing all of these different cases. So usually when you draw a triangle, you can label your angles and your sides using letters, and we label the angles with capital letters, and we label the sides that are opposite that angle. So opposite this angle is this side here, so we call that one A. Opposite of this angle is this side here, B, and opposite of this angle is this side here, C. And now there's this little table that discusses all of the different possibilities where well, it's not a little table, it's a bit of a big table actually, and it shows all of these different cases, and I don't know how any student is supposed to remember all of this. It's way too complicated. I never learned it this way when I took trigonometry. Um, I'm not going to encourage you to memorize this whole table or to even look at this table. What we're going to talk about is how to actually try to solve a triangle when you're given the information, and then just tell, are there any triangles at all that can behave like this? Maybe not. Is there just one triangle, or is there more than one triangle? And instead of trying to figure that out from, is the side A less than B and is the angle bigger than 90, we're just going to use the law of sines and we're going to think about it. And the main thing is that the angles of a triangle can't add up to more than 180 degrees. And it's going to be much simpler than trying to work through a table like this. So if you're getting a table like this in your class, throw it in the garbage, follow the advice that I'm giving you here, and you will be able to do everything that's in that table without having to even think about it. You'll just think about it in a more logical, straightforward sense, instead of following some table that's made there. Okay, so how can I select that? Let's get rid of that. And let us erase this. Okay. Maybe I can even copy this over. Oh, that'll be nice. Oh, there we go. Okay. So that's just a typical triangle. It might look like this really, or it might look something like that, depending on what the actual numbers are for the lengths of the sides and for what these angles are. So it's nice to draw a sketch just to sort of write something down about how the triangle is looking and then get your information on the paper. But the actual shape of the triangle might be a lot different than the sketch you guess at. And that's okay. You're just making a sketch before you actually know what the triangle looks like. Okay, so that's the general form of the triangle. One other important thing we're going to use in our work is the fact that for any angle, I'll call it theta here, but really theta is then, any of these three angles in the triangle. And for any angle theta, the sine of that angle obeys this relationship. So the sine of theta is the same as the sine of 180 degrees minus theta. And I'm working with degrees here. There's other units for angles, notably radians. All of this applies for radians as well, but of course you would put a pi there instead of 180 degrees. Okay, so for example, sine of 50 degrees is going to be the same as sine of 180 degrees minus 50 degrees, which is sine 130 degrees. So sine 50 equals sine 130. That's just the way sine works. I could do a whole thing about unit circles for you if you're interested in that sometime, but When I was in grade 12, we spent the whole time learning about unit circles, and I think it was really useful. But just to show you, so I've got my calculator set to degrees. That's important. There's these other units called radians. Uh, if you don't know what that is, you just want to make sure that your calculator says DEG. It'll say RAD for radians if it's in radians. But sine 50, okay, I got 0.766 approximately. Sine 130, 0.766 again, exactly the same. So it's no coincidence, and it works like that for any angle theta that you can think of. So, I just put 50 as an example, but it works for any angle theta. So I just showed you that in the calculator just to convince you a little bit. All right, so let's get rid of this. And the one other piece of, mathematical tool that we're going to be needing is the law of cosine, or the law of sines. There's a law of cosines as well, but we don't need that for this. The law of sines says that the length of that side A divided by the sine of that angle, capital A, is going to be the same as the length of the side B divided by the sine of the angle B. And I could put in something, you could put C in there as well if you want, but usually you're only working with two of the sides and angles at once. You don't need to get all three in there at the same time. So let's just keep it with A and B. And if that's true, I can flip both sides of that equation upside down and it will still be true. So we also have that sine A over A is the same as sine B over B. Okay, so you can write it either way. Usually it's easier if the thing you want to find out is on top of the fraction. So if I want to know the angle, I'm going to write it this way. If I want to know a side length, I might write it this way. And with an equation like this, there are four things I potentially don't know: the two side lengths and the two angles. As long as you know three of them, you can find the fourth one. And because this is true, there are some times that there's two different angles that can make the triangle work out. So those are the cases where there's two possible triangles that result. We'll also see some cases where no triangles are possible. Let's just go through some specific examples, and we'll do one case where there's, no triangles possible, another case where one triangle is possible, and a case where there are two triangles possible. Okay, so first let's look at a triangle with one side length of 7, another side length of 3, and an angle of 100 degrees, opposite of side A. Now you can go look up in the table like the one I erased, and it'll tell you how many triangles you should expect, but what I'm saying is let's just do the math and then trust yourself. We'll just check how many triangles are possible instead of trying to work with a complex table like that. And this way we really only have to remember this and the law of sines, and also remember that angles of a triangle have to add up to 180 degrees, always. Unless you're in curved space, but that's something for graduate school. Okay. So let's just do a little sketch. It's always nice to do a sketch. 100 degrees is a wide angle. It's bigger than a 90-degree angle. Let's draw it like this. We'll call this side 7. Here's 100 degrees. And we also know that one of these other sides is 3. Okay. Let's see what we have. So let's call this angle B and try to figure out what that angle B can be. So I know that sine 100 degrees divided by 7, so this angle divided by the length of the opposite side has to equal sine of B divided by 3. Okay, so if this is true, then I just have to multiply both sides of the equation by 3. You know, the 3 here, 3 here. These ones cancel out. And then sine B will be 3 divided by 7 times sine 100. Okay, so let me just write it out this way. Sine B will be 3 divided by 7 times sine 100. Let's figure out what we get here. So 3 divide 7 times sine 100. So my sine B can be 0.42206. You know, approximately. I didn't write down all of the decimals, and even my calculator doesn't show all of the decimals, so you'll always make a small approximation there. And now once I have what the sine of the angle is, I can find what the angle itself is by doing the inverse sine of 0.42206. So I just leave that in my calculator, hit second function sine, and that'll be the inverse sine. And the way most calculators work is this will just do the inverse sine of whatever number was in there before. So this works out to be 24.96 I could write. If I want to round it off just to one decimal, I'll call that B equals 25.0. So B equals 25.0. Okay, so if 25.0 works, from here, 180 degrees minus 25 would give me the same sign. Okay, so B could be either 25 or it could be 155.0 degrees. Okay, so one of those two angles are possible to make this true, because both these angles have the same sine value, because sine of 25 is going to be the same as sine 180 minus 25. Just check if you want to be sure. Okay, so sine 25.422618. You can see it's not exactly the same as the number we had there because we made that small approximation. But let's try the other one. Sine 155.422618 again. So they both have the same sign. All right, now the thing is, one of those angles isn't possible. Can you tell which one? So A is already 100 degrees, and all three angles of this triangle, A, B, and C added up, have to be 180. So 100 plus 25 still leaves me some room to have an angle C there. But if B was 155, that's not going to work, because 100 plus 155, that's already 255 degrees. So that's too big. That can't be a triangle. So that triangle is no good. Just one possible angle there. So there we go. There's going to be one possible triangle that follows this given information. I didn't have to look it up in the table. The table would have told me that, but I just used, my thinker to realize that 100 plus 155, that's too big. That can't be a triangle. Only this one angle is possible. Okay, so we've got B at 25. What's C going to be? C has to be, uh, so A plus B plus C has to be 180 degrees. So that means that C must be 180. Maybe I'll quit writing the degree symbol here for a minute. Minus A minus B, and that is I don't want to make a mistake in the video. Sometimes I do things in my head and get the wrong answer. Let's just do it. 180 minus 100. Yeah, it's 80, and then minus 25. You get 55. Okay, so that last angle is 55. So basically we've already figured out that there's one triangle and these are the angles. The last question is, how big is that side C? And you can get that from the law of sines again. So to find that last side C, we can say C over sine 55 degrees. So I took this side length divided by that angle. It's hard to tell the difference between a capital C and a little c, but this is my little c side length. And that has to be one of the other sides divided by the angle. Let's just take this side and this angle, but now that I know B and this side 3, I could have used that as well. So you have a choice, but let's pick 7 divided by sine 100 degrees. Okay, so now to solve for C, I need to multiply both sides by sine 55 degrees. And this one cancels, and then, it shows up over there, though. All right, I'm just writing that out to explain a little bit. I've got a video on algebra that you might find useful. But now we have C equals sine 55 divided by sine 100 times 7. C equals okay, we have sine 55 divided by sine 100 times 7. And there we go, 5.82, let's call it. 5.82. All right. Your teachers will like if you put a little box or a line under your final answers, or just put your final answer up in a nice table here. So I'm going to say this side is 5.82. The angle B we said was 25, and the angle C we said was 55. And we even found it to the first decimal place. If I was being careful, I should have put a 0.0 there. Okay, so there's a triangle. You can always check these by putting that in the law of sines. Basically, any length divided by the side of the angle has to equal one of the other lengths divided by the sine of the angle, no matter what the triangle shape is. All right, now I went and messed up the zoom. Let's try to fix that. Okay, not bad. I guess I need this hand. Pan it down a bit. And let's do a couple more. This looks like it'll be a bit of a long video. Okay, number 2. So it'll be a different situation. I'm not going to tell you which one. I actually forget which one. Let's just figure it out. A equals 5, B equals 6, and the angle A equals 120 degrees. All right, at 120, that's kind of a wide angle. You know, bigger than a 90-degree angle. I'll draw it something like that. 120 degrees. Oh, it's not almost straight. I don't have the best tablet there, but it does. It'll do the job. Okay, so there's our side A, or angle A. Our side A is then 5. Let's put B equals 6 over here. We need to find that angle B, this angle C, and this side C. All right, we'll use that law of sines. We know the side A and the angle A, so that's the part of the sine law we know. Let's go sine 120 degrees divided by 5. Should be, well, I guess let's work on B next, because we know at least the side length for B. We don't know anything about C yet. You find the angle C once you know the angle B, and you know that they can all add up to 180 degrees. And then once you have the angle C, then you can find the side length C. Okay, so sine B, and then divided by 6. Okay, so sine B will be 6 over 5 times sine 120 degrees. Six divide 5 times sine 120. Ooh, that's a pretty big number for a sine. Did you know that the sine of any angle can only be as big as 1? Sine of 90 degrees is 1. Any other angle between 0 and 180 gets a lower value for sine. So already I know there's no angle that can make this true. So basically we have sine B is supposed to be 1.039. 1.039 approximately. I didn't write down all those numbers. And this can't be true. Can't be true. That means there's no triangles that are like this. 0. Because, so this can't be true because sine for any angle is always less than or equal to 1. It's even greater than or equal to minus 1. But that doesn't matter as much to you right now. But because that's bigger than 1, there's no angle B that makes that true. What's the calculator going to do if I try to do the inverse sine of this? Oh, it started smoking and exploded. It's like in the old Star Trek episode. Okay, no angles make that true. So it's not you doing something wrong. It's just that you tried to ask the calculator to find an angle that's impossible to find. So it says error 2. Okay, so just the final answer for that one is no triangles have A equals 5, B equals 6, and the angle A equals 120. None. So that's one of the cases where there's no triangles possible. I didn't need the table. I just got a sine that was impossible to be for any angle. It can't be done. Okay, let's do one more example. So we had one triangle. We had no triangles. I'm guessing this is a 2-triangle example. Okay, so let's do A equals 6. B equals 7. And we'll take our angle A to be 30 degrees. Alright, so this time A is kind of a narrow angle. Draw it like that. Oh, that's a beautiful triangle. Alright, 30 degrees. We got A equals 6. B equals 7. There's the angle B. There's the angle C. There's the side C. Okay, let's try out that law of sines for B and A and see what we get. So sine B divided by 7 will have to equal sine A, which is 30 degrees, divided by 6. Okay, so now this means sine B will be 7 divided by 6 times sine 30 degrees. And let's see what B can be. We have 7 divide 6 times sine 30. And we get 0.583 repeating. 0.583. That's right. Oh, one more 3. Just the more digits you write, the more accurate your final answer will be. Okay. So then we do the inverse sine. I'll just leave all of that in my calculator so it's a little more accurate. And what b's make this possible? So B is 35.7 degrees is one B that makes that true, 35.7 degrees. But we also have to consider 180 minus that, right? So 180 minus 35.7. That's 144.3. 144.3 degrees. Okay, so last time we ran into this with two angles, we found that, the angle plus the second option made the total angles more than 180, which was not allowed, right? Can't have a triangle like that. But this time, 30 plus 144.3, well, that's still under 180 degrees, so that leaves some room for an angle C. Okay, so this time, both of these angles are okay. So basically 144 plus 30 is less than 180, so that will still work. And 35 plus 30 is a lot less than 180, so that'll work as well. So that's actually two different triangles that have this information. And let's see what they are. So option 1, let's call it T1, triangle 1, has, let's say for this one, B equals 35.7 degrees. So C will be 180 degrees minus A minus B, 35.7. And that angle works out to be 180 minus 30 minus 35.7. So we get out 114.3 for the angle C. 114.3 degrees. So that angle C is pretty wide, right? Let's see how long that side C is. So the side length of C divided by the angle C has to equal, well, we could use A again. So the side length of A was 6, and the angle for A was 30. Sine 30 degrees. So C is going to be sine 114.3, forgot my degree symbol, divided by sine 30 degrees, and then times 6. Let's see what that is. Sine 114.3 divided by sine 30 times 6. And we get 10.94, let's say. Okay, so triangle 1 has B equals 35.7, C equals 114.3 degrees, and side length C is 10.94. So that's one possibility. The other possibility, triangle 2, is when B was 144.3 degrees. This time that angle C will be 180 minus A, which was 30 degrees, and minus our new B. This is a completely different triangle, different angles and side lengths for B and C. Even though A is the same, the angle B is different, and even the side length of B stays the same, but this time the angle is different. 180 degrees minus 30 minus 144.3 degrees, and the angle C is 180 minus 30 minus 144.3. There we get 5.7 degrees. Okay, so that's a really small angle, but hey, it's still possible. It's still a real triangle, even with its small angle like that. As long as the angle's not negative, we're okay. Okay, let me try to scroll this up. So there we got C. We just need to find the side length C now. So side length C divided by sine 5.7 degrees has to equal, we can use our A data again, side length of A divided by sine of the angle A. So C equals sine 5.7 degrees divided by sine 30 degrees times 6. See what we get. Sine 5.7 divided by sine 30 times 6. All right, so this time C is 1.19. Okay, so that's the side length C, that's our angle C, and that's our angle B. See, we got different B and C than last time, and this triangle would look a little different, right? So the side length C is a lot shorter than the side we found before. However, they both satisfy what was given for the question, which was, what's written up here. Okay, so everything we found on the right works for all of this data. There's just two different ways you can make that all work out. Okay, so there's 3 different types of cases you'll run into when solving these ambiguous triangles. I hope that helped. If there's a particular case you're running into that gives you trouble, you can send a comment and I can make another video that addresses that.